to do some phase change math. Something I really like this. I think you guys will be good. We talked about my ice cream lab where the kids would think that nothing was happening because the temperature didn't change. It stayed the same. But that is the case in all phase change activities. The temperature stays the same. This is the principle behind a double boiler pan. If you have a double boiler pan, a lot of times if you do anything with chocolate, they'll tell you to melt the chocolate in the top part of the pan. The bottom of the pan has water in it that keeps the chocolate from going over 100 degrees because the water's going to boil at 100, but your stove's going to be much hotter. Seventh there didn't seem to have any experience with double boilers, though, so I'm sure that just went right over your head. So, substance temperature stays the same during phase changes. If a substance melts, now it absorbs heat energy, and that makes sense because you're going to put energy in to get those particles to come apart. When a substance freezes, it gives off or releases energy, heat energy. And that also makes sense. If the particles are going to slow down and become a solid, they've got to lose some of that energy. If you look at these pictures that I used this morning with College Chem, a solid, we know, has a definite shape and a definite volume. They are in motion, but it's a very little. A liquid, the only difference between the two is liquids move enough that they can roll over each other. So they have to be in a container. Otherwise, they're still very similar to a solid in that they're tightly packed. A gas, they can move all over. They have an indefinite shape and an indefinite volume. So if you think of changing from a solid to a liquid, you've got to heat these guys enough, just enough so they roll over. And if you think of heating from a liquid to a gas, you have to put a lot of energy in to get them far apart. Okay? So that'll make some sense, I hope. Wrong one. And that's not it either. All right. The heat of fusion, we already talked about. That is the energy required to melt a solid to a liquid. We use delta H fusion, and its units are joules per grams. Heat of vaporization is the energy required to boil a liquid to a gas. We use delta H of vaporization, and the units are joules per gram. Okay? So, I think I already said in the video earlier that we use Q equals MCAT if we have a temperature change. But when something is melting or freezing, because there's no temperature change, we have to use Q equals Ma. All right? What are you talking about, Ma? Well, here is Ma for water. Here is the enthalpy or the heat of fusion for water, delta H of water, and here's delta H of water when it vaporizes. So this is melting, and this is vaporizing, becoming a gas. Okay? So what we're going to do now is we're going to draw a picture of what's going on here. All right? Here's our problem. How much energy is absorbed by 25 grams of ice? 25 grams of ice times the specific heat of what? Well, it's going to go from negative 30 all the way to 110. So it's going to have ice in the solid phase, water in the liquid phase, steam at the gas phase. So what are we going to do? Well, we have to break it up into different steps. First of all, this is our temperature. It's in degrees Celsius. Start with our lowest temperature, negative 30. Then a little ways up, put 0 degrees because that's the freezing point of water, melting point of water. Then put 100 degrees because that's our boiling point. And our highest temperature is going to be 110. During the time ice is being warmed, its temperature is going to change. It's only when it begins to melt that it won't change. So we can use MCAT here. We can use the mass, which is 25 grams. The specific heat of ice is given over here on the left. It's 2.05 joules over grams degrees Celsius. And our temperature change is 30 to 0, so we have a change of 30 degrees Celsius. If we do that math, 25 times 2.05 times 30, 1,537.5 joules. Once it hits 0 degrees, though, as it melts, the temperature is not going to change, so it's going to flatline. This is energy down here, by the way. The temperature is going to flatline. This is where we're going to use MAW. So we're going to use our mass, 25 grams. This is where we have ice melting, so we're going to use the heat of fusion, 334.0 joules per grams. If we do the math for that, 25 times 334, that gives us 8,350 joules. I need to make this a little bigger. All right. After it's completely melted, the temperature will go up, and it'll go to 100. So we're back to MCAT. 25 grams times, of course, it's liquid now, so we can use our old friend 4.18. And we're going up 100 degrees Celsius. And we get 10,450 joules. Once we hit 100, we're going to flatline again because we're going to change phases again. So as we flatline, we have to use MAW, 25 grams. I'm actually going to move this over and do it on this side so I have more room. 25 grams times the heat of vaporization, 2,260 joules per gram. It takes a lot more energy to make a molecule water become a gas. All right, if we multiply that out, 25 times 2260, the energy involved there is 56,500 joules. We're not done. Once it's all steam, it can begin to heat up again, and it heats up to 110 degrees Celsius. At 110 degrees Celsius, we can use MCAT again, 25 grams. The specific heat of water is 2.05 grams, 9 grams. And the temperature change is just 10 degrees Celsius. And that's 522.5 joules. Now, if I want to have a little space, I'm going to copy these and I'm going to move them down here. And I'm going to add them up. So I'm going to take 522.5 plus 56,500 plus 10,450 plus 8,350 and 1,537.5. So if I add that up, I end up 77,360 joules, or 77.4 kilojoules, if you want a more manageable number. Okay? See, it's kind of fun. It's like a little puzzle. we can get rid of those now. All right, let's try another one. How much energy is needed to raise the temperature of 80 degrees gold from 875 to 1120? So we're going to start at 875. Is gold going to be a solid, liquid, or gas there? Well, since the melting point of gold is 1064, it'll be a solid. I'm going to write the melting point in here. And our last temperature, 1120, it's not going to reach boiling, so we aren't going to have as many sections as we did with the water. So, if it's a solid, it can change temperature. So we're going to start with our mass, 80 grams, times the specific heat of gold when it's a solid, 0.129 joules over grams degrees Celsius, times our temperature change, 1064 minus 875 is 189. Okay, our next segment is while the gold is melting. So we'll use MA. We still have 80 grams, but now we're going to use the heat of fusion of gold, 62.95 joules over grams. Grams cancel. 62.95. And that gives us, I'm going to move these because I can. 5,036 joules. Our last segment goes up to 120. Now we have gold as a liquid. The heat of fusion of gold that is a liquid, or not heat of fusion, the specific heat is 0.157 joules over grams degrees Celsius. And our temperature change is 1120 minus 1064, which is 56. Times 80 times 0.157 is equal to 703.4 joules. Now we add them up. 703.4 plus 5,036 plus 19,500. I didn't space that very well. Do you hear my stomach growl? I have to go straight from here to soil class and dig a soil pit. 3. If I did the math right, which I'm not making any guarantees about because it sure doesn't look right. Oh, there's a decimal there. If I did the math right, there you go. This will not be on the quiz. For homework, you're going to do the back of the worksheet you got today. The back says specific heat and heat capacity practice problems. There's 5 of them. You can do it. That's your homework assignment. Your homework quiz tomorrow for Friday will be over that assignment. All right? Well, not that assignment, but it'll be over Q equals MCAT. No MA in there. Monday, you guys will work on the next 2 worksheets, or the next 2 pages in your packet, pages 11 and 12. All right, friends. Thank you very much. Behave yourselves.